Doesn't work.
Yeah, it's working.
It's work. Okay.
Give it a minute, I'll walk around and see what.
I definitely want to play some. Years. I mean, it was my parents and they have summer house and I didn't see. So it's not ideal. Kids are
Am I in charge? Are you in charge?
No, you are in charge.
I'm in charge. Excellent. Okay, let's thank the speaker. Are we waiting for?
Should we pass this around at the beginning?
Oh yeah. Should we
Simon,
tell people what it is and then pause it? Is that the LIGO thing?
Yeah.
Okay. Do you want to talk about it?
Okay, very briefly. So, there will be a group going to the LIGO Hanford site on Saturday morning. Hanford is about 3.5 hours back from here, one day. We plan to leave maybe around 9, return by dinner time, so we'll have lunch either on the way or near Hanford. There are some of us who already signed up here for the first of the 2 trips. The first one is this coming Saturday on 12th of July. And so I'm right now looking for maybe the first, yeah, good, go ahead and sign. So I'll pass this sheet along. If you're interested in joining us, then yeah, either say yes or mark a tick against your name. The cost will be split among the visitors. So this primarily is the cost of the vehicle, rented vehicle, and whatever lunch you're going to have. So Jim will start with.
Incidentally, shouldn't we share also the cost of your wedding?
I think he was going to, he was going to give a.
How about we do that in the discussion session?
Okay, sure.
Yeah, that would be a discussion. How much money do you want to give to Satya? Okay, we start now?
Yeah, I'm going.
Right. So you can pass that around as we go along. So our speaker for this afternoon, well, it's up there. We're all very excited about this quantum K part, I think, because we don't know where.
I'm going to explain.
So Kenta will tell us about this thing. Talk is about half an hour thereabouts, plus discussion, or half an hour with discussion, or whatever it's going to end up being. So
Okay, hi. First of all, I would like to thanks the organizer for providing me a chance to talk in this workshop. I am Kenta Kiuchi from Yukara Institute for Theoretical Physics in Kyoto University in Japan. And today I'm going to talk about our latest research of the merger of magnetized binary neutron stars. We have performed a high-resolution numerical relativity simulation on the Japanese supercomputer K. By the way, this is a logo of the K, and this Chinese character means a 10 to 16 because K is a 10 petaflops supercomputer. And this work is in collaboration with Kotaro Kyutoku in UWM, Yuichiro Sekiguchi and Masaru Shirabata in YATP, and Tomohide Wada in NAOJ. So I don't think I have to talk much about the motivation of this work because you know well. So, and Steve has given a nice review in this afternoon. So one thing I would like to stress again is that the binary neutron stars are attracting attention as a possible site of the heavy element. During the binary neutron star merger, a significant amount of the matter could be ejected, and the amount of the ejecta varies from 10 to minus 4 to 10 to minus 2 solar mass, depending on the equation of state of the neutron stars. So inside the ejecta, the all process elements are synthesized, and the radioactive decay of these elements could be a strong and transient electromagnetic source. The so-called so-called kilonova or macronova has been proposed by Lee and Paczynski in 1998, and a number of people has explored the kilonova emission from binary neutron star merger theoretically. So one.
Sorry, Kenta, there was a statement which is very interesting to me, which you haven't mentioned. Kagra will be in operation to
2000.
Is that?
But just 1 month observation.
And with what sensitivity this is?
I don't remember the value exactly, but this operation will be done in a room temperature. And just one month observation.
So, but when is it that we should expect Kagra to be, really doing
around 2017. Okay, one of interesting candidate of the 18. One of interest candidate of the electromagnetic counterpart is GLB 130603b, and this is an observational image of this event at optical band and near infrared band at 9 days after birth and 30 days after birth. And if you subtract this image from this image, you cannot see a point source in optical band, but you can see in near infrared band. The right-hand side figure is a light curve of this GLB, and you can see an observational point in the near-infrared band. We have performed a numerical relativity simulation of binary neutron star mergers, as well as a photon radiation transfer to explain this light curve, and we have found if this GLB is driven by the binary neutron star merger, the ejecta mass should be as large as 10 to minus 2 solar mass. So it is mandatory to construct a physically reliable model of binary neutron star mergers, and Kyoto numerical relativity group is tackling this problem from two directions. One direction is based on the MHD, and the other is a neutrino radiation transfer. And today's talk is basically focused on this issue. So the reason why we consider the magnetic field is quite simple, as you know, because it has been observationally established that the neutron stars have a magnetic field from 10 to 11 to the 10 to the 15 Gauss, as this PP dot diagram shows. However, it is not clear what the role of the magnetic field during the binary mutation. During the binary neutron star merger is. The primary reason is that several magnetohydrodynamical instability, which have a potential to amplify the magnetic field, is activated by the short wavelength mode. And in addition, the dynamical range of the binary neutron star is quite large, from order 10 kilometers to several thousand kilometers. So we have to do a simulation which resolves the magnetohydrodynamic amplification process, and which covers these large dynamical range simultaneously. So in this project, we utilize a Japanese supercomputer K, which have a 660K cores, and this is a picture of the K. And this project is one of the subject of the high-performance computing infrastructure strategic program field 5. And this is outline of our numerical relativity code. We are implementing a nested grid to resolve the black hole, neutron stars, and gravitational waves simultaneously. The spatial scale of the former is 10 kilometers, and the spatial scale for the later is several 100 kilometers. The time step is limited by the speed of light, and we need a special prescription to interpret a magnetic field on the refinement boundary to preserve the divergence-free condition and magnetic flux conservation simultaneously. The numerical relativity simulation is a large byte per flops, and empirical communication on the refinement boundary is complicated, which could be an obstacle to the good scaling. However, we have conquered this problem, and our code is scaling up to the 80,000 cores with execution performance is about 15%. So let me show an overview of binary neutron star merger. This is a schematic picture of the binary neutron star merger, and this direction is the time directions. And if the separation between the two is fairly large, this is called this phase called in spiral, as you know. And the gravitational waves carry away the energy and angular momentum from the system. The separation between the two gradually decreases. Then the merger happens. So after the merger, you can see several passes according which determined by the relation between the total mass of the system and the maximum mass of the neutron stars. Because of the observational evidence that the maximum mass of the neutron star should be greater than about 2 solar mass, and the observational evidence that observed mass of the binary neutron star is clustering around 2.6 or 2.8 solar mass, and this central path is likely to be realistic. In this path, a hypermassive neutron star is formed after the merger, and this star has a rapid and strong differential rotations. Because of the gravitational wave, because of the angular momentum transport due to the non-axisymmetric structure of hypermassive neutron star, as well as the gravitational, there was an angular momentum loss due to the gravitational wave emission, it collapses to a black hole surrounded by a massive accretion torus. So in this talk, we mainly consider along this realistic path. So because of the limitation of the computational resources, we have decided an in-depth resolution study by changing the finest resolution from 70 meters to 150 meters. Note that the radius of the neutron star is 10 kilometers, and the highest resolution of the previous work is about 180 meters. So we implemented a nested grid to cover the neutron star black hole and the gravitational wave simultaneously, and we set the finest box as a cubic of 70 kilometers, and the closest one is about 4,500 kilometers. We have performed a long-term simulation of about 100 milliseconds in physical times. We choose an equation of state as H4 in our fiducial model. We set a equal mass system of 1.4 solar mass case. And the initial magnetic field, maximum magnetic field of the initial maximum strength of the initial magnetic field is 15 Gauss.
Where?
Inside a neutron source.
Is it 10 to the 15 everywhere, or is
No. I think it is hard to see, but this is a magnetic field line. So magnetic field line is confined. Confined inside a neutron stars, and not everywhere, locally.
Is it dipole magnetic field?
Not dipole, because it is very difficult to treat a magnetic field outside of the vacuum region. So it is confined inside a neutron stars.
Dipole on inside.
Yes, not normal dipole, confined dipole.
Are they cylindrical? How should I think of them? When you said 44 or 80 kilometer cube.
This box? Sorry, say it again.
Yeah, so what's the geometry of the box?
A box is a cubic box. geometry of the numerical simulation box is a Q.
So how many refinement levels do you use?
7.
7.
Yeah,
Okay.
typically 7.
And you run with 16K. No, sorry.
This 16,000 cores on gate. So let me show the visualization of our simulations. And this shows the isodensity contour, and purple color means magnetic field strength. So the separation between the two gradually decreases because of the gravitational wave emission, and the magnetic field doesn't have an impact on that in-spiral dynamics. This is a density, but purple is magnetic field strength. Okay. This is magnetic field strength. And then the merger happens.
And you're ignoring thermal effects?
No, it includes thermal effects. We use a piecewise polytope plus the gamma thermal equation of the state. And gamma thermal is index of the gamma thermal is 1.8. So. Oh. It's okay. Let me show again. So then the merger happens, and hypermassive neutron star is formed after the mergers. And okay, hypermassive neutron star is formed. And if you look at the so if you look at the instance of the mergers, you can see the Kelvin-Helmholtz instability is developed in the shear layer because you have a shear motion. Here, this is a shear motion, and this color shows the magnetic field strength, and the magnetic fields are amplified by them because the Kelvin-Helmholtz instability produces vortices in the shear layers. Then inside a hypermassive Okay.
You say that there is an instability because I can't tell with the color codes how much the magnetic field changes.
Is amplified. We're gonna show later.
I'll try not to do that.
Okay, and the magnetic field lines are wound up inside a hypermassive neutron star because this star has a strong and rapid rotations, and the magnetic fields continue to be generated inside hypermassive neutron stars. And you can see the density structures are symmetric, and angular momentum transport by the gravitational torque, and angular momentum loss due to the gravitational wave emission. Then in this model, the black hole, the star collapses the black hole at about 10 milliseconds after the mergers. And the high density materials are swallowed into the black hole, and it forms accretion torus around it. And inside, typical density of the accretion torus is 10 to 10 or 10 to 11 gram per cubic centimeter, and typical magnetic field strength inside the accretion torus 10 to 15 Gauss or 10 to 16 Gauss. And as you can see in this visualization, the magnetic field topology is mainly toroidal, and this configuration remains up to the end of the simulations.
This is just magnetic field strength, right? So
Yeah. This purple color is just a magnetic field, but I will show the magnetic field lines later. Okay, let me discuss about the evolution of the magnetic field energy. In this plot, we plot the three different resolution: 70 meter for color for the 70 meter, blue for 110 meters, and green for 150 meters. And this capital P and T symbol means a poloidal and toroidal component, and the time coordinate is shifted to align the time of the merger to be 0. and these dashed lines are black hole formation time in each lens. And you can see magnetic field amplifications depend on the grid resolutions, and we're going to explain one by one. The first amplification process is at the instance of the mergers. And as you see in the animations, the Kelvin-Helmholtz instability is developed in the shear layer, and vortices are produced. And this energy shows the higher the resolution is, the larger the amplification of the magnetic energy at the merger is. And this amplification process is proposed by the Ratio and Shapiro, and Price and Rosberg have simulated the Newtonian SPH simulation of magnetized binary neutron star mergers. And the left-hand side figure is magnetic field strength at the merger on the equatorial orbital plane, and you can see the magnetic field are produced in shear layers. The central panel is an evolution of maximum magnetic field strength, and you can see a steep increase at the merger as well. The Giacomazzo and Luciano and their collaborators have simulated numerical relativity simulation of magnetized binary neutron stars, and they observed amplification due to the Kelvin-Helmholtz holes at the mergers. However, the amplification factor in both simulations differ significantly. And one of possibility of this difference is might be a difference of the treatment of gravity, because Kelvin-Helmholtz vortices disappeared within the dynamical time scale of 0.1 millisecond, and the gravity of the general relativity is stronger than the gravity of the Newtonian gravity, so the approaching motion is faster than in the GR case, faster in GR case than in Newtonian case. So that time scale of the time scale in which the vortices disappear is shorter in GR case.
So Kenta,
yeah.
I'm speaking on behalf of also the authors of Price and Rosberg. I don't think their data should be taken any seriously.
Is that speaking on behalf?
I met with I met with Price in 2 weeks ago, but he didn't say nothing.
Didn't tell you that? Okay, that's
he
what
didn't.
told me.
He didn't
So
say
don't
nothing.
even cite me. But I mean, it's obvious from this figure, right?
This figure.
Their calculation is not even convergent.
Yeah, that's right.
So,
that's right.
I think they have published that paper, but I don't think we should compare with them or try to find a complex explanation why the time.
Did you say they have published the paper, but?
Well, I don't think we should consider it
also a good
seriously.
sentence.
I mean, or find a complicated explanation. And I don't think we say in the paper that we see the Kelvin elements. Actually, we say we don't see the Kelvin elements, or that is to. I think we see some amplification, but there are two effects happening there.
Mm-hmm.
You are compressing fluid there. And so inevitably, in the ideal MHD, you're going to have the magnetic field, the macromagnetic field just jump up.
But in that case, the amplification factor doesn't depend on the resolution, right? Because compression, if the compression...
If you, that should not be dependent on the
resolution. But in your case, very strong depend on the grid resolution.
Yeah. So I'm not saying you are not seeing that.
Okay.
So we were not seeing that.
In one of Bruno's recent paper, I was showing that if you went to local simulations, you were seeing even larger amplifications. You need very high resolution to resolve it. You know that compares to the resolution used here, which is already larger than most GR simulations. But
which one?
They're using 70 meters. I don't think we're going that. I don't think we're going as high as 70 meters. They're using 70 meters. I don't think we're gonna.
No, but I mean, in Bruno Giacomaso simulation, but in collaboration with people who do local box simulations. Was it Andrew Italian maybe? Yeah. And they showed that there was a huge growth of magnetic field in local simulations that was not reproduced in the global simulations.
Do you remember the amplification factors? I mean, how?
This is a paper published.
It was presenting at the EPS.
Yeah, could have been.
I remember the paper of Overgaulinger.
Yeah.
In 2009. They did the same. This is local simulation of Kelvin Hertz, and they were seeing basically growth in magnetic field up to the, a fraction of equipartition with the.
Yeah, I was just wondering whether you would think that 7 meters is enough to resolve that effect, or if we still need to go farther if you actually want to resolve it.
This okay. Let me explain our results. So, okay, this is a field line and the field strength in the shear layer at the merger, and right-hand side figure is an amplification factor of magnetic field, dependence of the amplification factor of magnetic field, and you can see the higher the resolution is, the larger the amplification factor is. And the amplification factor doesn't significantly depend on the initial magnetic field. Okay, so we conclude that all the feature we have found in this simulation is consistent with the Kelvin-Helmholtz instability, and this is the first point in my talk. Okay. Okay, the second point is in hypermassive neutron star phase. And this is a field lines and the density isocontours, and you can see a turbulent state inside a hypermassive neutron stars. And this hypermassive neutron star is differentially rotating, so it is unstable against the so-called MRI, and the magnetic winding for the magnetic winding works as well because of the rapid differential rotation and large value of the radial magnetic field component. So we suspect that the magnetic field amplification inside a hypermassive neutron star is caused by the MRI, and we foliate the hypermassive neutron star in terms of the densities, and in terms of the in the MRI, the fastest growing wavelength of the fastest growing mode is proportional to the magnetic field strength, and the inverse square of the density. So we foliate the hypermassive neutron star in terms of the density, and this left-hand side figure is the density contour of the hypermassive neutron star on the meridian plane. And we calculate the magnetic field energy in the range between the 10 to 11 to the 10 to 12 gram per cubic centimeters. And you can see that in the medium and in the high and in the medium resolution, the magnetic field energy is significantly amplified. But in the low resolution lung case, you cannot see amplification in magnetic field energies. So we have checked we can resolve the MRI or not by calculating the MRI length divided by the grid resolution, and then we found that in the medium and in the high resolution lung, this condition is satisfied, but it is not in the low resolution lung. Note that we calculate the wavelengths of MRI by the toroidal magnetic field strength, and the amplification growth rate of this amplification is about 100 hertz, which correspond to the several percent of the angular velocity of the hypermassive neutron stars. So and this figure is the same plot as previous one, but for the highest resolution model with changing the foliation in terms of the densities. And you can see that in a relatively low density region, such as blue, green, and red lines, you can see a significant growth in magnetic field energy, but you cannot see in high density regions such as cyan and magenta. So we conclude that this amplification is caused by the non-axisymmetric MRI, which suggests that the growth rate of the magnetic field amplification is several percent of the angular velocities. And the magnetic winding works as well for the toroidal fields because of the large value of the angular velocities and the large value of the radial magnetic field strengths.
Can you go back to the this one? So if I compare blue and green, I see that they start differ around about 3 milliseconds after the merger, right?
Yeah.
So that means that already at 3 milliseconds after the merger, the MRI should be active in the blue and not in the green.
Yes, but in this phase, the state is very dynamical state. You can see. Okay.
So let me ask you the question first.
Okay.
So I would say qualitative dynamics starts at 3 milliseconds, and that means in the blue there is something. Let's call it MRI. Then why is it that the growth rate of the MRI at 3 milliseconds is considerably different from the growth rate at 10 milliseconds?
This one.
Yeah.
And I think you asked the growth rate here and the growth rate here.
So which of the two is MRI?
We conclude this growth is caused by the MRI
What is it then?
Because in around 10 milliseconds, the hypermassive neutron star is quasi steady state. So, but in this phase, hypermassive neutron star is very violent and dynamical, very dynamical. So, in such a background, I don't think the perturbation analysis works.
So are you saying that in between?
But this is speculations. I don't have a.
So remember the discussion we had last week about F1 being produced. So would you say that between 0 and 5 milliseconds is when you have these large F1, F1 peak oscillations, and this doesn't?
Okay, this is a gravitational wave spectra, and you are discussing in this point. Okay, and this is a grid resolution dependence of the gravitational wave spectra, and this point doesn't depend on the grid resolution significantly. Okay.
No, of course. But so are you saying that you don't see MRI there because this stage is still very non-axisymmetric, or is?
Could be.
Plus, the magnetic field might have to sort of get organized for the MRI.
But
it never does. The green just stops organizing itself at that point.
So the green was too coarse.
Yeah. So there is
the green
definitely
is
something that the green is lacking, right?
Well, this is the typical thing that happens with MRI. If you don't resolve it,
that's
it does nothing. If you resolve it, then it starts growing.
Yeah, but it starts growing at 3 milliseconds, not at 10.
Well, then probably. I would say it's MRI from 3 milliseconds, but I don't know.
That's what
I don't know this. I don't know this.
But then, if it is MRI already at 3 milliseconds, what is the right rate?
Well, the fluid may still be compressing at that point, so maybe you have just the growth of the magnetic field from compression. If you look at the gravitational wave signal, it looked very different for the first 3 milliseconds.
Okay.
Yeah.
And this one.
Yeah,
right in there.
Plus 3 milliseconds. Yeah.
So I don't know what that means.
Okay. This is a final snapshot of the black hole and accretion torus with magnetic field lines. And magnetic field lines is mainly toroidal and less coherent structure in the poroidal directions. And during the hypermassive neutron star phase, a significant of matter is ejected outward and blown outward. And resulting lump pressure of such a resulting lump pressure due to the forward motion of such a matter is as large as 10 to 28 times square centimeter in our simulations. So, because we impose the ideal MHD condition, the magnetic field lines are frozen into the fluid element. So, that means that you need a poroidal motion to make a poroidal magnetic field and to overcome such a larger lump ratios. So, but it is non-trivial to drive such an toroidal motion in this simulation and in a shorter time scale. So let me summarize the magnetic field amplification during hypermassive neutron stars. As we explained, the Kelvin-Helmholtz instability at the mergers and MRI inside a hypermassive neutron star significantly amplified the magnetic field. Then the magnetic field energy is saturated at the black hole accretion formation times. Now, if you look at the low resolution LAN, you see the magnetic field is amplified inside a accretion torus, which is caused by the MRI inside accretion torus and the magnetic binding. However, our simulation shows that such an amplification is less likely. Okay, let me summarize my talk. We have performed the high-resolution simulation of magnetized binary neutron star merger in the framework of the numerical relativity, and we discussed about two ingredients of the magnetic field amplification process. One is a Kelvin-Helmholtz instability at the merger in a shear layer, and the other is a non-asymmetric MRI inside a hypermassive neutron stars. And these two processes greatly amplify the magnetic field, and the magnetic field energy is almost saturated at the black hole formation timings. So, okay, and we have found that it is necessary to launch an outflow, toroidal motion outflow to build up global toroidal magnetic field. Okay, that's all. Thank you for your attention.
Plenty of time. Luciano has already fired his initial parting shots with the paper was published, but
so Kenta, in the amplification that you are seeing, this is small scale magnetic field, so very turbulent, or do you see some global magnetic field also?
We don't. Okay, in toroidal direction, yes, but in toroidal direction, we don't observe a coherent magnetic field.
Okay. So that when the field amplification occurs, you said it occurred at relatively low density. What is the energy density in the magnetic field compared to the energy density in matter?
Matter in this model.
Yeah. So where the field is growing, is it gone past the virial
No.
Local virial limit, or is it still
Local? I don't check the local, but in global, the answer is no. I think the several % of the kinetic energy of the hypermassive neutron source.
In the high resolution, sorry, in the high density region, the region there is no growth, that the line speeds are resolved, or is it just that there is no growth?
In this purple region, the angular momentum is almost constant because this is a very deep inside a hypermassive neutron star. But in this cyan region, it is marginal. So because the wavelength of the MRI is proportional to the inverse square of the density, so in this case, the wavelength is too short to resolve even in our highest resolution model.
So you would expect it to be unstable in the CN2 normally?
Yeah.
But not in
we expect. Actually, we changed the magnetic field, initial field of, we changed the magnetic field strength of the initial field, and this corresponds to the effectively increase or decrease of the resolution for the MRI, right? And in this very ultra strong magnetic field case, we observe the magnetic field is amplified in these regions. Okay, but in lower, weaker magnetic field model case, we didn't see amplification in this red region. So that is a consistent.
And in all cases, you still don't see any global toroidal field?
No. In all cases, we don't.
Yeah, I just have a comment about this Price Roscoe paper. At Astronam a few weeks ago, Price publicly said that his simulations are wrong because he had problems with boundary conditions.
Yeah,
This
which
was
is what
a public statement
Okay.
that he made.
But wait, but this is a
He always
local effect. What do the boundary conditions do to this? If you got a local.
Yeah, but but this sample,
He's not using MHD. He's using this. What is it? Ernst's potential or whatever.
Yeah.
Oh, I see. Okay,
So everything is based on the boundary condition of these potentials, and which.
Sorry, boundary condition of what? Of
I don't know.
where?
This is what he said publicly.
Yeah, Kelvin-Helmholtz instability is a local.
But the Kelvin-Helmholtz is, it's a fluid instability. The growth of the magnetic field, that's how you couple your fluid to the magnetic field.
Yeah.
In their prescription, they're using, not using MHE, they're using, I can't remember the name of this potential, but they're using a formulation in which you write a colloidal and toroidal field in terms of potentials, on which you impose boundary conditions at the boundary, and those were the wrong boundary conditions.
Okay.
But I think we shouldn't discuss this. If the author said it's wrong.
Okay. Let me change my statement. So our results support the ratio and the Shapiro result.
Now let's see each other. Do you want to take them on?
Okay. So yes.
So what kind of physics, microphysics or plasma physics input do you think your simulations would be sensitive to, and
microphysics?
For the magnetic field evolution, is there anything that you would like the physicists
we don't incorporate the quantum effect of the magnetic field, because this magnetic field is above the QED limit. So, that's the first point.
So you think you understanding the electron-positron pair production in the large magnetic field case is going to be important?
Might be, but I don't know how to do it.
And
I had
do
to
you see
implement.
any sensitivity to the equation of state? I mean, if you were to do this with a very different low-density equation of state. My earlier question was I was just wondering whether if you had 10 to the 14 Gauss or 10 to the 11 grams per centimeter cube, the equation of state knows nothing about it, right? At 10 to the 14 grams and 10 to the 11 grams, the equation of state is not even correct. And,
Not even wrong.
yeah, I mean, it's just not even wrong.
Yeah.
So I just want to know whether you can map out the regions where you can compare locally the pressure of matter or energy density of matter with the magnetic energy density to see whether there is some physics that can be introduced into this code.
Yeah, maybe. Yeah.
So is it easy to do? Can you just make a plot sometime?
Yeah, I can make a plot, but I have not. But yeah, I'm gonna check it. Yeah.
So about your jet, okay? You said you can't launch a jet.
I can't.
We also can't launch a jet. What we produce is a magnetic field, poloidally dominated magnetic field structure. And as you said, producing this poloidal magnetic structure, you need essentially to have fluid elements that are launched along the edges of the torus.
Yeah.
And that's what we see. We see that there is a very strong wind on the sides of the torus, which takes toroidal magnetic field and just stretches it out. And so I was wondering, if you were to calculate your magnetic field lines putting seeds much closer to the to the aperture of this cone, so very close to the black hole in a very small cylinder around the axis of the black hole, and maybe if you look at different times, because at different times you might have different magnetic field lines, maybe you will see.
But we've checked the velocity field of the matters, and the basic direction. Sorry. Okay.
I think the remote has a.
Okay, velocity field is in this direction, in this direction. Thank you. This one. Okay.
Which is a bit strange because
in this snapshot.
Also,
but if you wait for a long time, you can see such a motion.
So can you see, if you look at, you said you've gone to 100 milliseconds.
Yeah.
What does this look like at
100,
90 meters?
but 100 second for the medium resolution case. But in high case resolution, we don't. We didn't do such a long-term simulation.
What is a typical Lorentz factor you obtain?
Very low, 1.2 or 1.3 or something like that.
We get 4, so maybe that is a difference.
Oh yeah, yeah.
Can we go back to your very nice movie? When you produced the affirmation neutron star, I saw there was a clear
Asymmetric.
That's right. It was an m=1 mode.
Yeah.
But I thought you said they are equal mass.
Equal mass system.
So what produces the m=1 mode?
Wait a minute. m=1 mode. The reason why we observe m=1 mode, I don't have a definite answer, but the one possibility is low T over W instabilities, because hypermassive neutron space has a very rapid and strong differential rotations. And the other thing is the effect of the magnetic field, because that strong magnetic field, toroidal magnetic field, is subject to the kink instability. That's right.
So if you concentrate on the m=1 deformation, how does this change with resolution? Does this become stronger and stronger with resolution?
I have not compared exactly, but in very low resolution case, we didn't observe the m=1 deformation. But in that case, the resolution is 300 meters or 400 meters, something like that. Yeah.
I have the same question, but I have another one. Do you think you're getting close to a point where you can start making predictions that might interest observers of any kind?
Observable. Observable.
We make predictions all the time. It's just
that's why I added the last bit.
Because Steve have discussed about the precursor due to the magnetic field during the inspiral phase, but we estimate the Poynting flux at the end of the simulation, but we didn't observe any coherent magnetic field in our simulation. So the Poynting flux is very small in that case.
Well, everything's confined to the stars for the pre-merger.
No, but I talked about after the mergers in this phase. In this phase, yeah.
What about the ejecta? How much, did this give out more ejecta compared to previous?
No. Dynamical ejecta doesn't depend on the magnetic field strength.
Okay.
Strength.
What is the typical amount of ejecta you found, the upper limit of the ejecta, from 1% of the solar mass?
In binary neutron star case is 1% of the solar mass. Yeah.
You said the ejecta doesn't depend on...
Yeah, that doesn't make sense. That's not right.
Yeah, that doesn't sound right. Post-merger, the ejecta? The
Post.
ejecta is a very small effect, and these magnetic fields are going to...
Yeah. Ejecta of the dynamical component. Ejecta the matter which is ejected at the mergers.
So it's not the wind-driven.
Not wind-driven, dynamic.
The magnetic-driven wind. Sorry.
And what was your initial magnetic field strength?
10 to 15 Gauss.
So if you increase that a little bit, it potentially could affect.
But I think the difference is lower than the numerical accuracies. In this model, the typical the dynamical eject amount of the dynamical ejecta is 10 to -3 solar mass. So
you're just talking about the unbound matter?
Unbound matter. That's right.
Kenta, can you go back to the magnetic field evolution and black hole formation?
Animation?
Maybe the previous one. This one. So the green.
This one.
the green collapses earlier than the red, but then the blue collapses.
Ah, okay, okay.
So you know, let me ask you a question. The standard law is that MRI drives, you know, angular momentum outwards.
That's
so
right.
How do you explain that the green collapses earlier than the red? Or
I can't explain why this. Okay, one is magnetic pressures.
Angular momentum.
Right. So in principle,
the other is that mass is ejected outward. So this means that mass is become lower.
So can you?
So
if you concentrate on the angular momentum distribution.
Then so collapse should be earlier.
Right, but can you see that the angular momentum is actually distributed outwards?
By mass ejection, so mass is become lower. Then so collapse is delayed. It's not very easy.
It's easy. It's simple. It's not simple.
Right,
so
but
probably use similar things.
The final.
We try to you know, with Kiki. Kiki, you. But with Kiki, we tried exactly to study this by looking at the angular momentum distribution as a function of time, to see whether it's actually moving inwards or outwards, and I think maybe Kiki will present this. It's a very interesting diagnostic because you learn where is the angular momentum going, and it's, as Masaru said, it's a complicated balance between.
Yeah.
You are producing more magnetic field, and this is giving you pressure, but you're also moving angular momentum outwards. Furthermore, you're losing mass. It's okay.
Complicated.
I just thought you had a clean description of what is going on here.
Is the ejector converged? I mean,
Ejector can ejector can converge. Yeah, almostly.
Okay. Right. Shall we maybe thank our speaker again?
Thank you.
And shall we have a little break? You want 10 minutes?
Yeah. We'll convene again upstairs
Okay,
and
so
see.